like a type of problem like that one?
Sure. All right. The thing about number 8 too, so it says, so the problem for those of you that don't have your book open is use analytic methods to find the intervals on which the function is increasing, decreasing, concave up, concave down. Support your answers graphically, then find any local extreme values or inflection points. So the function that we're given here is y equals x over x cubed minus 1. And then to find all of this stuff, obviously we're going to have to find the first derivative and the second derivative. So let's just get right into it. So y prime is going to require the quotient rule, right? And so we'll take the bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be 3x squared, divided by the bottom squared. All right, and because ultimately we're going to want to use this, derivative, we should simplify and clean it up here. So x cubed minus 1, that's not going to change, minus 3x cubed. So ultimately that's going to be negative 2x cubed minus 1. Minus 3x cubed, yeah, minus 1. And that's going to be divided by x cubed minus 1 squared. Okay, so there's our first derivative. Second derivative then. This should be fun. We've got bottom times the derivative of the top. So x cubed minus 1 squared times the derivative of the top is going to be negative 6x squared. I think that's it. Minus the top times the derivative of the bottom. When we derive the bottom, we're going to get 2 times x cubed minus 1 times the derivative of the inside, which is x cubed, so times 3x squared, all divided by the bottom squared. All right, clean it up. Not much we can do with this first part. It's just going to be negative 6x squared times x cubed minus 1 squared. There's no reason to FOIL this out at this point, I don't think. Okay, what can we do here? Let's distribute the negative through. So we'll get plus 2x cubed minus 1. We'll have 2 times 3 is 6, so we'll have 6x squared here and x cubed minus 1 here, all divided by x cubed minus 1 to the 4th power. There's a factor of x cubed minus 1 in each term here, so there's, well, it's actually 2 of them here. There's an x cubed minus 1 here and 4 of them down here. So we can eliminate those simplify to 1. All right. We can also continue to make this better. I mean, I'm hesitant on how far I want to go with simplifying the second derivative because I'm probably not going to actually analyze concavity with the second derivative. But anyway, you could factor out the 6x squared here out in front. And if you do that, okay, I guess I'm going to do it. I can't help myself. I'm going to factor out a 6x squared. That'll give me 6x squared out in front of everything. I'll be left with a negative x cubed minus 1. So if I distribute that through, I'll have negative x cubed plus 1. And then when I take an x squared out of this factor, I'll be left with 2x cubed minus 1. So plus 2x cubed minus 1. That's all divided by x cubed minus 1 to the 3rd power. If I make a mistake, yell at me here. This is going to get even better. So negative 1 plus 1 is 0. You've got 1x cubed times 6x squared. So ultimately, your final, your most simplified second derivative is going to be 12x to the 5th divided by x cubed minus 1 cubed. Yeah, I know. Okay, so there's your second derivative. Wonderful. Questions on the first two derivatives? All right, so let's spend some time analyzing the first derivative, and then we'll kind of call it good there. The second derivative analysis is similar. So first derivative, again, so we've got it in front of us, negative 2x cubed minus 1 divided by x cubed minus 1 squared. You don't have to do this, but I'm going to factor out a negative from the top. Ultimately, I'm going to be analyzing the sign of this thing. So I want that. All right. Next, if I'm trying to find intervals of increasing and decreasing, I want to know where the critical points are, because that's going to tell me where there's a switch from increasing to decreasing, or vice versa, or possible, well, any horizontal asymptotes. So let's start with, when does f prime not exist? Okay, well, the only situation where that will happen is when the denominator is equal to 0. So we want to know, when is x cubed minus 1 squared equal to 0? That's going to be whenever x cubed minus 1 is equal to 0. That's going to be whenever x equals 1. Okay, so there's one critical point right there at x equals 1. All right, then we want to know, when is the entire derivative equal to 0? So when does f prime equal 0? Well, that's going to happen whenever the numerator is equal to 0. So whenever negative 2x cubed, oh, hold on, this should be plus. I factor the negative out. Always feel free to interrupt, guys, if you see a mistake. We'll save us time later. All right, so we want to know when this is equal to 0. That's going to be whenever 2x cubed plus 1 is equal to 0. Subtract 1 divided by 2, I get whenever x cubed is equal to let's see, negative 1 over 2. Take the cube root of both sides. So I get whenever x is equal to the cubed root of negative 1/2, whatever that is. All right. So there's my other critical point. Questions on getting the critical points, or any mistakes that you saw I made? Okay, so then let's finish out the first derivative analysis here. That number line is probably too big. So we got our two critical points, which is x equals 1 and cube root of negative 1/2. I don't know exactly where that is. It's to the left of 1. It's to the left of 0 as well. So we'll call it right there. Then I'm going to check points to the on each interval. I'm going to plug them into the derivative to figure out what the signs are. Okay. So this is cube root of negative 1/2. So I think negative 1 has to be to the left of that. So we can plug negative 1 in here. If I plug negative 1 in up here, I'm going to get a negative negative 2 plus 1 divided by, if I plug in negative 1 here, I'm going to get negative 1 minus 1 squared. So let's just write that down, negative 1 minus 1 squared. The bottom is going to be positive, so we can sort of ignore that. The top, though, this will be negative 1 inside. Negative 1 is positive 1, so we have positive over a positive. That would be positive. Questions there? All right, I know that 0 is between this number and 1, so I'll pick 0 for that interval. I plug 0 in here. It doesn't matter. This will be positive. If I plug 0 in here, I'm going to get a positive number, positive 1, times a negative. So that'll be negative. So I'll have negative over positive. So we've got decreasing right here. And then if we switch to an interval over here, I'm going to plug in 2. If I plug in 2 in the denominator, I get a positive number. If I plug in 2 here, I'm going to get a positive plus a positive times a negative. So it'll be negative again. So negative right here. So we know that we have our intervals of increasing are from negative infinity to the cubed root of negative 1/2. That's it. And then our intervals of decreasing are from cubed root of negative 1/2 through 1, and then also from 1 to infinity. You do have to break them up like this. Turns out not only does the derivative not exist at 1, but obviously the function doesn't either. Wait a minute, where's my original form? Yeah, the function doesn't exist at 1 either. There's a vertical asymptote there. Okay, so you do need to break up the intervals like that. You do the same analysis for the second derivative. So just sort of save time, I think I'll leave that. What do my professors always say? I'll leave that exercise to the students. All right. Questions?